Okay, so hello and welcome to this new lecture in the ongoing series of lectures on digital prepress. Today, we will be starting our discussion on scanners. I've already told you, I think, the mechanism and the working principle of scanners earlier in the prepress inflow class. Okay, so I'm not going to talk a whole lot about the working principle, which you already know. But I will focus my attention on some of the scanning mechanisms or what are the parameters that you need to keep in mind while scanning the originals for digitization purposes. Okay. Now, but before that, as always, I will like to give you a very brief overview about the scanning principles as well. So, as you can see on your screen right now, primarily we are having two types of scanners. Okay, one is a flatbed scanner, another is a drum type scanner. Here in the case of your flatbed scanner, what is the principle? This is a glass panel and you have to put your document facing this glass and cover it up and then you scan it. So what must be the principle? There must be some, so this is the glass, so your document is facing downwards, that is facing the transparent side of the glass. Now this is some illuminant, this is throwing some light onto the document and the reflected light is being captured by a series of photosensors. So for a flatbed scanner, we know that we are using CCD sensors, right? And there are color filters available which will channel, which will differentiate between the various wavelengths of light that is incoming or that is getting reflected off from the surface of the document. And as a result of which, because there are color sensors available, you can get a colored image out of it. There is a 2D converter which converts the electrical energy into electronic energy and then electronic signal, sorry, and then you get the final image. We'll see how basic operation of how that works later on, but this is the overall mechanism. This is the overall method of scanning, or the basic working principle of a flatbed scanner. For the drum scanner over here, as you can see, what you do is you simply wrap around the original. This is the image that is given over here. This is somewhat uh, similar to that of a external drum scanner, where the image or the artwork has to be wound around the cylinder, this cylinder, with facing which is facing outward. There is a illuminant which is throwing some light on this particular artwork, and there are the light which is reflected from the surface, that is again being captured by a photosensor and then sent to different color sensors, so that separation of the colors may be done and you get a color image. The film scanners, you see, is, I think we have got a one duo scan, Agfa duo scan in one of our labs, that is capable of scanning both reflective copies. So this is a reflective type scanner and this is a transparency scanner. So film scanners, the films we call as transparency, that is why these are known as transparency scanners. So what you do is you place the image on a flat bed. There is a illuminant on one end, and the light will not get reflected off like in drum scanner or your flatbed scanner, but it will pass through the transparency and then get captured by your photocells. Okay, and then it will again pass through the various color sensors. So this is how the film scanner or transparency scanner works. This is an overview about all these three types of scanners and the working principle of different scanners that you are seeing in front of you. Okay. Next, the camera. We are not really talking about the cameras right now because principally they might be the same, but ultimately what difference there is that for a scanner we can very precisely control the um, image quality in a scanner, right? When you take my elective in the final semester, we will be talking about what is the method to calibrate and characterize various imaging devices. There you will see There's a basic difference between I'll just give you a brief overview why we are not really talking about cameras here, and we're only talking about scanners. See, there's a very basic difference between both of them are imaging devices, right? Input devices. They are digitizing some image. So for your scanner, you've got your uh, some transparency or some reflective copy. You are digitizing that, and your digital camera is digitizing a natural scene. That is the only function, right? For both of them. Therefore, they are input devices. But the primary difference between, and imaging technology is somewhat also similar. There are sensors which captures light, and there are filters which separates the light into different color channels, etc. So that is also somewhat similar. But the primary difference between a scanner and a camera when we are talking about color management is that we need to characterize, we need to calibrate. So these terms may not be that familiar with you: calibrate, characterize. Just to give you a very brief idea, uh, calibrate means to bring your device to a known state of functionality. Okay, so um, and characterize, for that matter, is to get your device to a certain state of working condition. Okay, where the output is from the device is as per your expectation. So this is a very brief uh, overview about what calibrate and characterize means. These are two different terms. Okay, so they're often used uh, together in the sense that one has to be done after the other. So first you need to calibrate, and then you need to characterize your device, imaging devices. Now, as I was saying, that you need to calibrate and characterize your scanner. But for cameras, the purpose of calibrating and characterizing your scanner is to get your device to a certain known state of working condition, or to tweak or modify your output to a certain known state. But for cameras, it is not required to do so. We are not required to do so always. We may calibrate our cameras just to get to know what their working state is, but we may not need to characterize our cameras, because cameras are used for clicking pictures, and afterwards they are being edited. Especially digital images today are heavily edited after they are being taken on a camera, taken through a camera. You have software like Lightroom and Photoshop and all that. So you are editing your image for this purpose, to this end, that the images that you take through a camera, you need to make those images aesthetically pleasing. You don't want, you sometimes want originality, or you want to capture what was actually happening when you took the photo. But most of the times when you're using a camera, the output needs to be aesthetically pleasing. It may not be as similar to the original scene uh, uh, as you want, but the end result that you want from a digital camera is that you want to get a picture which is looking good. For scanners, we don't want that. This is the basic difference. We'll come to that when we are talking about in the elective class, but this is not the place. That is why I'm not really going into the entire thing of the cameras. But let us talk about how the sensors work. So this is one example. So here you see, this is a very nice image that I have chosen over here. This is something which is, I think, I don't know if you know this, but this is known as the Bayer filter. A very popular filter, color filter, which were used in cameras. Nowadays, a lot of other filters are there also as well. This is another type of triple sensor filter. A Bayer filter, you will see, for every uh, single red sensor, there are two green sensors, and for every blue sensor also there is two green sensor. Our human eye is more sensitive in the green region of the visible wavelength. That is why any small change, this is very useful information when we study colorimetry later on in PMS2. Our eyes are very much sensitive towards green color than in any other color. That is why any small difference in green color is very much easily caught by the eye. That is why in Bayer filter, the number of green cells or the number of green sensors are quite large than in case of your than in comparison with your blue and red sensors. Okay, but nowadays, if you remember the other picture that I showed you during classification of classification of your graphics, you see, if suppose this is a pixel array, then each of the pixel has got three sensors. Most of the sensors in the displays at least work on this principle. There are other deviations also, as you can see in front of your screen. Okay, now let us talk a little bit about what are the determining factors in terms of the quality of your image when you scan your particular image. We will talk about how to tweak or how to modify the image quality when you scan your originals, and what are the parameters that you need to be careful about while scanning your originals. But this is a very kind of a bird's view of what are the determining factors that control the quality of your scanner. First is mechanical and electronic factor. Mechanical factor is, so I don't know if you have noticed, is if your scanner has become very old, then the scanning bed may get deteriorated, and the movement, if somehow the movement of the sensor array which scans the original, that gets in poor shape, then there will be streaks, banding appearing in your scanned image. That is a problem. Electronic factors is limiting factors, like what is the resolution, scanning resolution, maximum scanning resolution of your scanner. Next, photo multipliers or CCD. So depending upon, there is a efficiency of both the sensors are different. Whatever scanners you are using, they will the ultimate quality will change. Range here basically means it is another they are, what they're trying to say is that resolution only, what type of resolution they are offering, and how many tonal values can be created with that particular scanning machine. Okay, then number of bits per basic color, that is bit depth. This is nothing but, this is what bit depth they're talking about. Okay, whether your scanner is able to scan in 8-bit mode or 16-bit mode. As I told you earlier also, that for most of our test target printing in color management, we need 16-bit images, 16-bit TIFFs and 16-bit EPS files. Next, resolution. I'll talk about resolution in the upcoming slides. And finally, image scanning software. So depending upon what manufacturer you're using the scanner of, their interfaces will differ, and some of the advanced scanners, they offer a lot of functionality, inbuilt functionality in the software that comes along with the scanner, which will help us to change the quality of the, or modify the quality of the scanned input uh, as we please. Okay, next. Yeah, so this is, as I was talking about. Now from here on we will be talking about a little bit about the resolution. Okay, so one, let us get certain terminology quite clear at this point in time. Okay, so for us, we already talked about the half tone screen resolution. What was the unit for half tone screen resolution? It was LPI for AM screens, and micron for FM screens, right? So we are not considering FM screens right now, we are only considering AM screens. So LPI, lines per inch, how many lines are there per inch of the screen? That is the resolution of your half tone screen. Then we have what? Then we have PPI. PPI is for what? Your scanners. How many pixels per inch? Okay, and scanners or displays also, you can include displays also, since we will not be talking about displays, because we will only be talking about our scanners. That is why I wrote scanners, but it can be carried on with displays also. Then we have another term which is DPI. DPI is for output devices. What are the output devices? CTPs. We'll talk about DPIs at length when we talk about CTPs and what is addressable resolution and all in the upcoming lectures. Now, take a look at all the four images. I mean, yeah, all the four images that is given over here. What is so let me just tell you that what it all means. First, this is the original actually. They have been broken down into smaller components. I hope you are understanding what you are looking at. So this has been broken down, the entire image has been broken down into some few blocks. Alright. Now ultimately, what is the output? This is the output. And in this case also, this same image has been broken down into uh, some blocks, and overall output is this one. Now what does it mean? What inference can you draw from this particular image that I just showed you? See, resolution ultimately is how frequently you can divide a particular image in context of scanning, in context of digital displays. Okay, so how frequently you can divide up a certain image. Here you see the entire image has been divided into 1 2 3 4 5 2 3 4 5 25 boxes, right? Now imagine this is 1 inch. Okay, just consider here for a minute. This is 1 inch. So what is the resolution of this particular image? 5 pixels per inch, right? 5 pixels per inch. And similarly the length remains the same for this image also. This is again 1 inch, but in this context, in this situation, the same image has been broken down into how many pixels? 1 2 3 4 5 6 7 8 9 10 10. So here the resolution is 10 10 ppi. That means 10 pixels per inch. If this distance is 1 inch, then the resolution here is 10 ppi and resolution here is 5 ppi. Now if we scan this original in 5 ppi mode, that means if you have seen the scanning head of a scanner, there is a long bar which is lit up and which scans, which moves from one direction to the other, scanning the entire document. There within that bar there are these sensors, okay, these photo sensors. In a one particular scanner, for 1 inch, let us say the bar is, let us say that is 10 inch. The length of that bar, scanning bar, is 10 inch. That particular scanner has got a resolution of 5 ppi. That means for each, let us say this is 1 inch, this is another inch, this is another inch. For within that 1 inch there are 5 photo sensors like this. Next again, for another 10 inch there is another 5 sensors. But for another scanner there the that is again 10 inch total distance or the length of the scanning head, but the resolution here is greater. That is, suppose this is 1 inch, then there are 10 such sensors within that 1 inch. That means what? This means what? This means that for any given image, what is the maximum resolution that this particular scanner, this is scanner 1 and this is scanner 2, for any given image, what is the maximum resolution that the your scanner 1 can provide? It is 5 ppi. Similarly, for scanner number 2, what is the maximum resolution that your scanner can provide? Scanner number 2 can provide, that is 10 ppi. So naturally, if the number of pixels which you are using to represent a particular digital image is higher, then naturally the color information or the overall information in that image will be higher. Greater the number of pixels, better will be the image quality. This is common sense, right? So ultimately, if you are scanning this image, the same image in both the cases, if you are scanning the image with first scanner, then the output you have only few number of pixels are there. But if you are scanning the same image with scanner number 2, then the number of pixels over here is very high. That means the color information, you can take a look here also. This is scanned with scanner number 1 and this is scanned with scanner number 2. In which case there are large number of pixels, in which case the number of colors is high, in which case details is high. Of course, the one which has been scanned with scanner number 2, because the input resolution means what is the inbuilt resolution of your scanner, that is high. So ultimately, scanning resolution is how much resolution or how many pixels there are per inch within that scanning bar of your scanner. Greater that value, better will be the image quality, greater will be the input resolution, or greater will be the resolution of your scanned image. Okay, that is what is being represented in this case. All right, next, yeah, here you see that in this particular case, that a pixel based image always has a set resolution, that is ppi, pixels per inch. In this example, the image has 8 pixels per 0.028 inches. That means if you convert it into 1 inch, that means, so for 0.028 inches, 228 inches, if there are 8 pixels, then for 1 inch how much pixels? That you will get as 350 ppi, that means pixels per inch. Okay, so this is what the resolution we are talking about. This is how we define resolution, that I've already told you earlier also. Okay, next. Yeah, this is another, so this is what I was talking about. You see, this is the scanning head. Okay, this is the entire scanning head. Okay, so you see, this is the length of the scanning head and this is the breadth of the scanning head. Now tell me something. And the document has been laid over here like this. The scanning head is moving in this direction to scan the image. Now, if I ask you from this image, is the scanning resolution same in both the directions? Both the directions means length as well as breadth. If I ask you, this is the length, this is the breadth, right? Now, if I ask you that is the scanning resolution same along the length and the breadth of this image, what will you say? No, obviously no, because you see, along the you can consider this. Okay, fine, consider this only, no problem. Along the breadth of this sensor array or this scanning bar, how many number of pixels are there, and along the length how many number of pixels are there? What will you say? Are they the same? No. In this situation, how many pixels are you can find? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And along this one, you can find only 5 pixels, right? For a unit length actually. So that means along one direction, the scanning resolution will always be higher than the other direction. It is possible to equate that also, but it is what normally happens for most of the scanners. That is why it is said that in some scanners the maximum resolution is indicated as higher in one direction than the other. This is because the row with CCD cells can be moved in smaller steps than the row's own resolution. The scanner can thus scan more tightly in one direction than the other. At the highest resolution, 2 pixels beside each other will be the same. So that means that is what this line is very much important. That this is because, see, this is because the row with CCD cells can be moved in smaller steps. That means what? So if you consider row means this is one row, this is another row, this is row, and these are the columns, right? Now, how many columns are there? 5 columns, and rows are 12 in this case. Here you see, why is it said that the CCD row, this is because the rows with CCD cells can be moved in smaller steps, because inherently, because of the design of the scanning bar or the CCD cells, the number of CCD sensors that is present along the row, or what I have written here as breadth of the cell of the scanner, is higher. There are larger number of cells, CCD cells, along the various rows of the scanner in comparison to the columns of the scanner. That is why in one direction we are getting greater scanning resolution in comparison to the other one, almost half. So if there are like so let us say that in for particular, this is just for example purpose, no scanner comes with a resolution of 12 by 5, but normally 600 you will see even in your home scanners and all those multitasking, those printers have got an inbuilt scanner. There also you will find 600 ppi is there, 600 dpi is there, because so here I am using the term PPI and DPI almost analogously, but these are different terms. So here let me only refer to as PPI itself. So in those scanners also you will find in 600 PPI or even 1200 PPI, but that resolution is along the breadth or row wise resolution. The Column wise resolution will always be lower in most of the case for our, at least for our home scanners, home multifunctioning printers, at least for them the resolution will be lower along one side and higher along the other side. So that 600 ppi or 1200 ppi, whatever you see, that is along the row of the scanning device. Okay, so hopefully this was clear, the importance of the scanning. So as we were discussing, the resolution, specifically the input resolution of our scanners, that is kind of an determining factor uh, while deciding the image quality, overall image, scanned image quality actually. So let us now take a look at how this is really determined. This is determined with the help of something which is known as sampling. Now, in the earlier slide, I had already shown you that ultimately the resolution is dependent on how many pixels are there, or how many, you can say, how many sensors are there per unit length, right? There is a physical limit to it. The maximum or the addressable resolution, you can say maximum output resolution or addressable resolution, there is a physical limit to it. What is that limit? That it cannot exceed the total number of pixels that is present in the scanner sensor array. So let us say there is a scanner which is having 1200 sensors per unit inch, okay, or per unit length. You cannot use that scanner to scan something at a resolution greater than 1200. Your limiting factor is 1200. But what you can do is, if you want, not every time we require a scanning resolution of 1200 ppi, right? In most of the cases we need maybe so much lower than that. Sampling determines what, sampling factor rather, determines how frequently we are screening the original image at. So that means it is basically something related to frequency only. So what is the scanning frequency, you can say, what is the input frequency with which you can scan your original. Now over here, if you see this type of a graph, now see this is the, let us say the you can say that this is basically the intensity, pixel intensity, you can say, or tonal value. Let us say this is the tonal value. This is a continuous curve, right? Now, in order to digitize it, you need to discretize it. Discretize means you need to break it down into some discrete signals. This is a continuous signal which you are getting from a continuous to an original, let us say, which you are scanning. But in order to digitize it, what you need to do, you need to divide it up into some discrete signals, right? One way of doing it is take few samples at regular intervals like this. You can take few samples and the intensity values of those intervals will be recorded as your electronic signal, which will be used for rebuilding your digital image or creating that digital image. Now here you can see that at regular intervals this almost looks like a histogram that I talked about earlier lecture, I think. So for this particular, all the pixel intensity values have been sampled at regular intervals, right? Now what you need to see is that at this particular interval, the pixel intensity value is, let us say, 0.1 unit. For this next interval it is 0.225 unit. This interval it is again 0.1 unit. This interval it is 0.6 unit, right? Pixel intensity values. So that means what? This is an image. This is a digital image which has got these pixel intensity values for this much amount of space. Let us say this is a rectangular image. This is a grayscale. So this particular grayscale has got its pixel intensity values different at different intervals. The primary difference between this image and this image is what? This is a continuous plot. That means this is a plot that you would normally get from a continuous tone image, where each point is having a certain unique value. But in this, when you are discretizing it or you are digitizing it, each point does not have a discrete value. That means all the points that lies in this interval has equal amount of pixel intensity value, that is 0.1. All the points lying within this interval has the equal pixel intensity value of 0.25, like this. So you have discretized it. You have broken the continuous tone signal into some discrete forms, into some unique values. Now, the question here, why I am talking about the sampling and sampling factor, is this will determine how frequently you sample these signals. See, you have got how many intervals here? 1, 2, 3, 4, 5, 6, 7, 8 intervals. You have broken down the entire continuous tone signal into 8 discrete steps. But in order, you can increase or decrease this frequency, right? In this case, instead of 8 intervals in this next scenario, you have got 16 intervals, right? You have got 16 intervals here, and you have got 8 intervals over here. So which do you think will have a better image quality? Obviously this one, which has got greater frequency or greater sampling. So this is where the sampling rate comes in. Sampling rate, if you want to define it, you can say that it is kind of a the frequency at which you are discretizing your original to digitize it. That is what sampling is all about. You can increase the sampling rate, you can decrease the sampling rate, that we'll see later on. But this is what sampling is. When you have got a original, which is a continuous tone original, so and you're getting an electric signal out of it, right? There is a to D converter there, and this A to D converter will digitize that electrical signal, right, which has been received by the photomultiplier tube or the CCD sensor. Now, how frequently will this continuous signal or this electrical signal will be broken down? What will be the frequency used? How many samples will it require to recreate this entire electrical signal? These are these intervals will determine how frequently, or the sampling rate will determine how frequently your signal is being broken down to recreate or digitize your original image. So this is what sampling, the background of sampling is. Now, this is kind of I have given you, so I'll just write it down: 1, 1, 2, 2, 3, 3. This is a kind of a mnemonic that I have drawn to explain how this works. If you remember my earlier lecture on histogram, I had shown you at the end, I think, of the histogram lecture, bit depth and histogram lecture, that how a 8-bit histogram differs from the 16-bit histogram. Maybe there are two images, same images, one have been downgraded to 8 bits and the other is in 16-bit. If you extract the histogram from the 16-bit and 8-bit, you will notice how different they are. If you consider that this is your 8-bit, let us consider this is your 16-bit image and this is your 8-bit image. Okay, now this is sampled more regularly or more frequently. The amount of data space that is present here is higher than what that is present over here. This means what? That the sampling rate in 2 is higher. So if the sampling rate is higher for any scanner, that means what? We are scanning the original using a higher resolution. So maybe this is scanned at 600 ppi or dpi, and this is scanned at 300 ppi. Okay. So naturally, when we are scanning something at higher resolution, we will get larger number of data sets. That means the sampling rate, that means the number of samples or number of discretized intervals in this particular scenario is higher than those obtained in this one. We have sampled this original at a higher rate than in case of 1, right? Isn't it? So that is what I have referred to in this particular image. Okay, and as you move on from 1 to 2 and 3 to 4, then the sampling rate is increasing. That means we are scanning the same image. See, the nature of the image is same, but we are scanning the image with increasingly higher resolution. That means we are increasing the sampling rate. There is always a limit. I have already told you what is that limit. Limit is the physical number of sensors that is present in the scanning head. That is your physical bar. You cannot exceed that. You cannot, if your maximum scanning resolution of your scanner is 1200 dpi or ppi, then you cannot scan something at 12 more than 1200. You have to, the maximum limit is 1200. But all that I am talking about now is what you can scan at lower than that. Not everything has to be scanned at 1200 dpi. I will, in the later sections of these lectures, not this lecture, maybe perhaps like next lecture, I'll be talking about how in which scenario we need to scan at lower resolution, we need to print at lower resolutions, in which scenarios, and why, how can that be achieved using our some calculations. So, but the concept of sampling is how frequently you are breaking down the continuous electrical signal that is obtained as a result from the CCD or the PMT sensors in the scanner. How frequently you are breaking down that continuous signal, and this will determine if you are breaking down that continuous signal using multiple, very many number of intervals. In case of this 4, in comparison to 1, see the sampling rate in 4 is much higher in comparison to 1. That means what, you have, the signal remains the same, but while breaking down, while converting it, while digitizing that signal, you have chosen greater number of sample space or intervals while scanning in this scenario, fourth scenario, than in first scenario. That means the ultimate resolution of the scanned image in case of 1 will be lower, and the scanned resolution in case of 4 scenario will be greater because the sampling rate is higher. Okay, ultimately the resolution will become higher as you increase the sampling rate. Okay, now, so this is what the overall effect is, right? So as you go on increasing the sampling rate, obviously since the number of information, number of sample space is higher, number of intervals is higher, the overall resolution will increase, and as a result of which, what will happen, the image quality will increase. But when you are choosing a lower sample rate, the number of intervals will go down, and as a result of which, the overall image quality will go down, because there is not enough number of samples or enough number of intervals to display your image. So your resolution will suffer, your image quality will suffer. Okay, so yeah, this one, now we are slowly and steadily, although now we will not directly use the concept of DPI because we have not come to that point yet, but let us still define and these particular terms. Okay, so let us start with LPI. I will start with LPI because we know what LPI is. That means lines per inch. Dot size varies, but lines, that is center to center distance, remains the same. How many lines there are per inch within a linear inch, that is used for as a unit of measurement for measuring the resolution of your half-tone screen. For those scenarios, we use the unit LPI, with lines per inch. Okay. PPI is any digital display. You are seeing this image. That resolution is defined in PPI. That means how many pixels are there per inch to display the image. If the number of pixels is lower, then resolution will go down, and the image will look like this one, right? There is not enough number of pixels to display your image properly. That means resolution will suffer. And finally, we have got DPI. DPI is in terms of what we are printing, maybe on a piece of paper or on the CTP or on the film, etc. That is dots per inch. We will talk about DPI at length at a certain point of time later on. Okay. Now, here just although you know this, but let me just go ahead and show you this. For news, as I told you, that not in all scenarios we do not need a very high resolution. For newspaper, its quality is relatively lower than what has to be printed in a packaging or in in other publishing good quality books, etc. Because it's a daily print. So naturally the screen resolution required for newsprint is lower. For uncoated paper, it is lower in comparison to coated paper. For coated matte paper, the resolution is lower, but for coated glossy paper, when we are using, the screen resolution or screen frequency has to be very high. Why? Because when we are choosing a coated glossy paper, like a gloss art paper, then it is considerably assumed, or we can assume it, that the quality of the job that we will print is quite high. As a result of which, if we do not increase the screen frequency, the quality will go down. That is why we need to use a higher resolution screen. Okay, next. So yeah, now now we know what sampling is, right? So it is kind of clear to us, and we have also seen that earlier also, that when we go on increasing the sampling rate or the sampling factor, that means when we sample the analog signal very frequently, that means it has got higher sampling factor or higher sampling rate, then the resolution or the overall output quality of the image will go up, it will increase. But here in this image, it's a very interesting curve actually. This is the, along the x-axis we have got the sampling factor, and along the y-axis we have got the perceived quality. So the question is, what is perceived quality? The difference between perceived quality and actual quality. What is the meaning of this term perceived? Perceiving something. How we are seeing something, how we are visualizing, how it is appearing to our eyes, the human eye. That is what the perceived quality is. And actual quality is what is the overall resolution of the image, what is the overall file size of the image. That is one, right? So from this curve, one thing is clear. What is that? That upon increasing the sampling factor or the sampling rate, the perceived quality will increase to a certain extent. You see, till 1.5, 1.75, 1.5 only, it has increased constantly, continuously. It has increased till 1.5, right? The sampling rate when it is 1.5, or even you can say more than that also, it has increased. It has increased at a lower rate, but nonetheless increased, right? So when we are using a sampling factor of up to 2, see, up to this point, the sampling rate has the quality, the perceived quality, most importantly, perceived quality has increased. So what does it all mean? That suppose we are scanning the same image at multiple sampling rates. First we are choosing one, we have scanned the same image at by choosing one sampling rate. And so how to determine the sampling rate? There are, for high-end scanners, the, as I already told you, the quality in one slide I showed you earlier, no, that the quality of the scanned image will be determined also by the scanning software that comes with it. So high-end scanners, their software interfaces that comes with the scanner, they have the provision of changing the sampling factor manually. Okay, not for the low-end scanners that much. So I have scanned the same image 3 times. One, by choosing the sampling factor of 1, second by choosing a sampling factor of 1.5, and third time choosing sampling factor of 2, right? So what will be the perceived quality in all these things? What among these 3 scans of the same image, whose quality will be the highest? Of course, from the curve it is quite evident that the image which you have scanned using a sampling factor of 2, that will have the highest quality, because perceived quality is increased. But what will happen after that? What will happen after that? So you again you use the same image for scanning, but you now choose a sampling factor of 2.5 instead of 2 or 1.5 or 1. It has been observed that after a certain point, no matter how much you increase the sampling factor, the overall perceived quality, not actual quality, perceived quality, what we will notice with our eyes, what we will observe with our eyes, that does not really change, that remains fixed. So if we have chosen a sampling factor of 2 to scan an image and another sampling factor 2.5 to scan the same image, there will not be much difference between the quality of the image in terms of what we perceive it. Of course, you can say that actual quality will increase. Why? Because with increased sampling factor, higher resolution image will be obtained, and you see the file size will go up. That is the same reason. See, after a certain point in time, nowadays these display manufacturers, they are going for 4K TV and 8K TV and this so many Ultra HD and Fantastic HD and all this. But after a certain point, you will not be able to really understand or distinguish the difference between a 4K image and a 8K image, because our eye's ability to resolve, we will talk about it, that is known something known as the optical transfer function. For cameras, we call this to be the camera's ability to resolve contrast. This is known as the modulation transfer function. For similarly, the ability of our eyes, the lens that is in our eyes, the ability of our eyes to resolve contrast, that is known as the optical transfer function. So there is a bar, there is an upper limit to it. So it is not possible for the TV, maybe the display may be 8K, 16K, so many Ks. But ultimately, if your eyes are not able to perceive the difference between a 4K display and a 8K display, there is no difference as such. So there is a limiting factor there as well. So when we talk about the various types of transfer functions, optical transfer functions, we'll talk about it. So that is what I mean to say here. So if you scan the same image once with a sampling factor of 2, another time with a sampling factor of 2.5, you won't perceive much of difference between the two images in terms of the image quality, visual image quality. Of course, the actual image quality will go up. Now the question is, so do I use a sampling factor of very high value if I am not getting any real perceivable difference in quality? The answer is no. That is why sampling factor, whenever we are using this, we have limited the sampling factor for scanning purposes to be 2. Beyond that point, beyond a sampling, when you are scanning something with the sampling factor greater than 2, then the overall image quality will increase in terms of file size. See, the file size has increased in comparison to when it was 2, sampling factor was 2, but the perceived quality, what you see on your screen, that will not go up. So what is the use of higher file size if you do not distinguish the difference between the two? So that is why we say that sampling factor, it is better to use a sampling factor of 2 if you are looking for good work. It is fine. I mean, beyond that point, there is not much difference in the perceived quality of the image. Now, apart from the sampling factor, there is another factor that you need to take care, or that is determining factor in determining the quality of the scanned image, that is known as the scaling factor. So scaling factor, I think most of you know, that is, we're talking about the degree of magnification. Remember in the earlier class I showed you in Photoshop that at what percentage magnification that you are viewing the image. So I think it was 66 or 67%. So scaling factor is somewhat similar to that. Okay, so the term scaling factor is actually means that to what extent you are increasing or enlarging the size of the image. There is a formula to find out what is the maximum scaling factor that you can use for your particular image and scanner combination. So as they have given over here, that maximum resolution of the scanner, maximum scaling factor, how to calculate that? Maximum resolution of the scanner divided by the image resolution. So let us say if your maximum allowable or addressable resolution for your scanner is 1200, then the the resolution of your image is 300, then 1200 divided by 300 is 4. So you can maximize it, or you can enlarge your image 4 times without getting that staircasing or that pixelated effect in that image. So ultimately, together, when you combine all these factors together, what information can you draw regarding the optimal scanning resolution? That is, in order to calculate at what scanning resolution you need to scan a particular image, that can be given by the screen resolution in LPI, what screen you are using, into sampling factor, which is, as I already told you, it is normally 2, into the scaling factor in percentage. Okay, so this is the basic formula for calculating the optimum or the resolution at which you need to scan your images. All right.